I made some new handouts here, so you should have 2 pages with you signed in. You got more? Thank you. Okay, good. Thank you. I'll bring them back. Okay, so there's going to be 4 different sections that we're going to talk about. The first one for this chapter is the Michelson-Morley interferometer, and it uses some of the principles that we learned from the double slit diffraction experiment. And we'll see more of that as we go on. Okay, so we started talking about this last time, and I will stop for questions after a few minutes, and we'll take pauses and try to digest this as easily as possible. The basic idea of the Michelson-Morley experiment is that there is a light source which is provided over here on the left, and light usually monochromatic, so we have a single wavelength lambda that is impinging on the light source. I mean on the apparatus. When the light hits what this is a half silvered mirror, silvered mirror, which has 50% reflection and 50% transmission. So it's equally reflective as it is transmitting. So the idea is that when light impinges on this half-silvered mirror, half of the intensity goes straight through, half of it gets reflected up to mirror M2. And on the return trip, the light coming back will recombine, will hit the half-silvered mirror, and some of it will get reflected down into the eyepiece or the observer. So there's either a lens or an observer. Try to draw like a Simpson figure. The observation plane, P, and the light intensity will change as the mirror this one within 2 gets displaced up or down by a given distance. We'll call it delta x. Now, initially, what we can view from this is that when L1 and L2, which is the distance from the silvered mirror to each of the reflective mirrors, when these 2 paths are identical, then the path length for the ray traveling up here and back is the same as the path length for the ray traveling to M1 and back. Therefore, when this one gets reflected from M1 and this one gets transmitted through from M2, they will be in phase and the intensity will remain bright. So in other words, when L1 is equal to L2, then the path difference is equal to 0, and therefore the phase difference, delta phi, is also equal to 0. And therefore, the intensity is a maximum. Okay? So, all this is saying is that if I split the light into 2 different paths and they recombine, and they both traveled the same distance, and they've both been going at the same speed, which obviously we believe is true, then they will recombine in phase. Any question on this? Right? That's to say that the sine wave of one will coincide with the peak of the sine wave of the other, and the sum of these 2 will be in phase, right? We get a bigger amplitude. Right? Everyone agree with this so far? Okay. Now, if I move this second mirror up the distance delta x equal to lambda over 4, then the ray that reflects up from this surface will have traveled a total distance lambda over 2 further than the ray coming back from this path. And therefore, they will be exactly half a wavelength out of phase, or difference in path length. Path difference will be lambda over 2, and so they will add and cancel each other. Okay? So how do I know that? Well, if I take that the phase difference is equal to 2 pi over lambda times the path difference, which we will call, in this case, it would be 2 times delta x. Then, and if 2 times delta x is equal to lambda over 2, then this becomes 2 pi over lambda, and this becomes equal to, 2 pi over lambda, and this becomes equal to pi, 180 degrees. Right? And we know that two waves that recombine 180 degrees out of phase cancel, the intensity goes to 0. Okay? So, that's what happens when I move this mirror up by a distance equal to lambda over 4. If I move it up another quarter wavelength further, then now the total path difference, the path difference will be, if delta x is equal to lambda over 2, then 2 times delta x is equal to lambda. Now this ray has traveled a distance lambda further than this true one, and so the phase difference between those two should be exactly equal to 2 pi, lambda times lambda, and so this is equal to 2 pi, and two waves that are exactly 302 pi radians out of phase add together constructively. And then I get an intensity. So this gives me an intensity minimum, and this gives me an intensity maximum, right? So as I move this mirror up by, I start here with a bright spot. They both travel the same distance. I get a bright intensity pattern. The two waves arrive in phase with each other, and I get a bright spot. I move it up a lambda over 4, then this light spot, this becomes dark. The interference cancels, there's no light getting through. Then I move it up another lambda over 4, and it gets bright again, right? So every time I move the mirror up by lambda over 2, so every increment, delta x, or I should say delta x equal to lambda over 2 means that at p comma, intensity goes from max to min, or bright to dark to bright, right? Bright to dark to bright. Right? Which is to say that the intensity goes from I max to I min to I max. Okay? So what happens if I do this 20, if I go to, I do this 20 times. So in other words, instead of moving it up by lambda over 2, I move it up by, I move it up by, let's say, 10 lambda. So let's suppose that delta x is equal to 10 lambda. Then what I will see is that the intensity goes through 20 cycles of max to min back to max again. Okay? So every increment of lambda over 2, I go from bright, dark to bright. If I go lambda, it'll go bright, dark to bright twice. If I go 2 lambda, it'll go bright, dark to bright 4 times. So I can see that the total displacement, delta x total, is going to be equal to lambda over 2 times the number of intensity cycles. Okay? Everyone see that? Every time I move it by a distance lambda over 2, then the intensity at this point goes from bright to dark to bright. So if I move it another lambda over 2, it'll happen twice. If I move it another lambda over 2, it'll happen 3 times. So the relation is that the total number of cycles, if I measure the total distance that I've moved it up, and I measure a number of intensity cycles that it goes through, then I can solve for lambda. Okay? So I can make a measurement of lambda and using this interferometer. And again, we always use the same thing we've been saying over and over again, that the path difference is equal to 2 pi over lambda. I'm sorry. The phase difference between 2 waves is equal to 2 pi over lambda times the path difference. It's exactly what we used for the double slit experiment. This is the same thing. And furthermore, in the double slit experiment, what I found with this is that the intensity, I equal to I0, expressed in these terms, is equal to cosine squared of delta phi over 2, where in our conventional use in double slit, I'm equating delta phi equal to delta, which was what we call the phase difference. And so, using this. So basically now I can plug this quantity for delta phi in here, and I'm using the same equation as we used for the double slit, and this becomes cosine squared of 2 pi, pi over lambda, actually 2. One second. 2 would be 2 pi over lambda times delta x. And so if I plot this out, then what I get as a function of delta x, which is the displacement of this mirror from the point where they were equal intensities, or equal lengths, is that what I will see is that the intensity falls off like cosine squared theta. It goes to a minimum, it comes back up to a maximum, it goes back to a minimum. So when delta x is equal to lambda over 4, since this is already labeled the delta x-axis, so when this is lambda over 4, then this goes to a minimum, and when this is equal to lambda over 2, it goes to a maximum, and it just repeats. Okay? So the repetition is exactly, or the formula is exactly the same as the double slit experiment, but the intensity is changing as the mirror location changes. Okay. Any questions on this? Does it seem clear? You in the front row? Yes?
An example would be good.
Okay, I will have an example. Okay. Yeah, okay, good point. So, if the observer, let's do one over here. So supposing the observer counts 360 cycles. So the observer moves the mirror, when M2 moves up by 0.1 millimeter, the intensity at P, point P up there, the screen, goes through 360 intensity cycles. Okay, and we know what a cycle is: max, min, back to max. Okay, and now I want to talk about what is the wavelength of the light. What is lambda? Right? What is lambda? Okay, so there's pretty straightforward. I put in this equation up here, the total delta x motion was 0.1 millimeter. This is equal to lambda over 2 times 360, and I solve for lambda, and get lambda is equal to 555 nanometers. So now we've done a problem where we've solved for wavelength. Okay. That's pretty straightforward, right? I mean, you know, and that's really all there is to using this, is that you measure as you move the mirror into a certain distance delta x. I count how many times the intensity changed from max to min, back to min, max to min, back to min, max again. And that gives me the formula then for solving for wavelength. Now in principle you could do this with one cycle, right? But let's suppose the error in your measurement was 1/8 of a cycle. Well, then you've now made almost a 10% error, 12% error. Whereas if I do it 100 times and my error is still 1/8 of a cycle, then now it's only 1/8 out of 100, right? So you usually want to count more than once to go one cycle. Okay. Okay, so now we get to fringes. Okay, up till now we've just talked about going from bright to dark to bright again. Typically they don't really use it that way. What we do instead is we call count fringes. Now conceptually or linguistically, when I say count fringes, you can think of cycles of max to min to max. They're identical. Okay, so if I said I'm going to count 20 fringes, that means I've gone through 20 cycles of max to min to max. But why do we call it fringes? Okay, so that's where page 2 comes in. Okay? Page 2 comes in. So on page 2, instead of having M2, the mirror be flat, what we're doing instead is we're putting an angle on the mirror. Right? So the angle, the mirror has an angle like sort of like this. Right? And now what happens is, now you have to look at your handout sheet, and everything I said about ray number 2, the middle ray, is the same as what I just said earlier. All right? Everything that you see as ray number 2 here happens exactly the same. As I move the mirror away by the center of that mirror by a distance of lambda over 2, then the intensity for that central ray number 2 will go from max to min to max. That's the same as what I said before. But now we're going to look at rays off to the left or right of the central ray, which I call ray number 1 or ray number 3. Because of the tilt in the mirror, ray number 1, the ray number 1 gets reflected at over a shorter distance than its ray that went straight on to mirror M1. In other words, if I track the path of the ray number 1, you can see that it has now traveled a shorter distance than the light that went straight through the mirror to M1 and came back. Everyone see that? That path difference for ray number 1 from the half-silvered mirror to M2 is shorter than the path difference from ray number 1 from the half-silvered mirror to mirror M1. Everyone see that? Path difference is shorter? So when that path difference is equal to lambda over 4, when ray 1 has traveled, ray 1 is split, right? So that for that ray, we will say that L2 is equal to L1 minus lambda over 4. Then that means that for that ray number 1, which is right here, it will have traveled a distance lambda over 2 less than this ray. So when these two recombine, if this one was a bright spot, which I'll call B, then this ray, when it recombines over here, is a dark spot, is a dark line. And similarly, if I have a ray that originates ray number 3 below the central axis. It gets split, and what happens there is, again, or in this case, the ray that is going up to M2 travels an extra path length, lambda over 4, relative to this ray that went through and came back. So they will arrive out of phase, and it will be dark. Similarly, if I go even further out, then the ray difference between these two paths gets even shorter again, and the path difference becomes half integer of lambda, so this becomes bright. And then it becomes dark, and then it becomes bright. So I get a pattern of bright, dark, bright. Bright, dark, bright, dark, bright, dark, bright, dark, right? Because rays from hitting different parts of the mirror are recombining at a slightly different phase, right? Or they travel different path length, and at some point they're going to cancel each other, and then I'm going to get that this is dark. So what I end up with when I look at this, the light at the plane of observation, which is where the observer is or where the screen is, what I'm going to see is a pattern of bright, dark, bright, dark, bright. You see this pattern exactly as you see here. Okay? Now what happens is I begin to move. That's a static picture of what's happening. Now what happens is now I move the whole mirror at an angle up by lambda over 4, and what used to be bright becomes dark, what used to be dark becomes bright, etc. So now what happens is the bright and dark spots have reversed. Right? When your eye looks at that, it looks like the bright spots have moved. Right? And if I keep moving delta x, keep moving mirror further and further up, it's going to appear as if these fringes are moving across the observing plane. Okay? Your eye, when you switch the bright to the dark, the bright to the dark, and the dark to the bright, it looks like the lines have been shifted. Anyone see that? So I can count fringes. And when I count fringes, it's like there's a crosshairs here. As I move delta x further and further away from the half-silvered mirror, then these bright lines cross the bullseye of the telescope. And so by counting how many fringes that or bright lines cross a given cross the center for a given change movement of the mirror, I can measure delta x by this motion. I can count fringes. Counting fringes is the same as number of cycles of bright, dark to bright. And so, again, I can use this equation, but it's a more accurate way of doing it. Okay? So your homework problems talk about fringes, and that's why I'm explaining this now. The way I learned it was this way, and the fringes are vertical. You can also create situations where the fringes are circles, and you can count the circles moving across the line, but a fringe is a fringe. That part we don't need to know. So everyone understand now when counting fringes is the same as counting how many times the intensity changes. Okay? Any questions on that? Okay. Now the reason this was so important was not because it wasn't particularly because this was a brilliant new way of measuring wavelengths. The reason this became important is that instead of using it to measure wavelengths, they were using it to measure what is the velocity of the Earth with respect to the ether. And the ether was this preferred frame of reference, which we'll get to in relativity, which basically said there's only one little frame of reference in the universe where Maxwell's equations and Newton's laws are valid. And anyone moving relative to that, right, will not observe those equations. They'll observe something else. So that preferred frame became known as the ether frame. Turned out that that was a false hypothesis. And that what Michelson and Morley showed was that the velocity of Earth with respect to the ether was 0. And basically what they did was they were looking at the fact that the velocity of light in this arm was different than the velocity in that arm. Now, we may or may not get to that part. I have a different way of presenting relativity, but the Nobel Prize portion of this was in describing how to measure the velocity of light in this arm versus this arm. And there was a way to actually do that measurement. And but it was a null measurement. And what that meant was that the velocity in these two arms were always the same, as we have just assumed here. We assumed that the velocity in those arms were the same. And so that's what we ended up with. I'm getting a very cold breeze. I don't know if this is coming in here or somebody. Feels like somebody has somebody's got a door open down the hall. It's 0 degrees outside. Okay, so that's what I wanted to talk about on that. And you have a couple homework problems to do, wavelength calculations. Okay, so the next thing I want to talk about is diffraction gradients. And I thought I had already loaded this, but it'll just take me a second. You can put the camera on hold, Ashwin. Our double slit experiments. So we basically found that if we had 2 slits in our opaque structure with light coming through, and I need my pointer. That if with light coming through, that, let me just draw the picture again in case you've forgotten what this looks like. You remember that if we had 2 slits, then the intensity pattern would be a cosine squared function, just like we were just talking about, right? We applied that actually to the Michelson-Morley experiment. Okay, so this is the intensity pattern, which is a cosine squared function of delta over 2, and delta is the path difference, is the phase difference due to this path difference, which, as we said, was d sine theta. Right? Now, it's important also to realize that we calculated where the maximum and minimum occurred. So in this particular diffraction pattern, we found that the minimum occurred at sine theta, and I'll call it sine theta 1 min. The first minimum is equal to lambda over 2d, and the first maximum, sine theta 1 max, was equal to lambda over d. Right? So for double slit, that's what we have. And for single slit, you remember the relations are reversed. We said that before. Okay, so so this is the scenario that we have. That intensity pattern is the one you see here. There's the central maxima, and there's the m equals 1 fringe, and this is the m equals 1 fringe on the other side of the center line. Now, it turns out that if we are able to go to 2 slit or let's say 6 slits, multi-slits, this actually shows 5 here in the sequence. This diagram is for 6, but the idea is more or less similar. What happens is that the location of the intensity maxima is identically the same, does not change, but the width of the intensity maximum gets smaller and smaller. So the idea of using multiple slits is that we're able to take each of these fringes and make them very narrow, very narrow. And that's useful because we'll get a more accurate measurement of wavelength. Because if it's a very narrow band width, I can measure theta much more accurately than if it's a very broad minute maximum. Also, if there are 2 wavelengths coming through at the same time, because in this scenario right here, we've considered there's only 1 wavelength, lambda, but what if then you could have a light source with 2 different wavelengths, lambda 1 and lambda 2? Right? So they're going to give different locations of the maximum, but if they're close together, you will not be able to resolve the difference between those two peaks. In other words, they will completely overlap and you will not be able to see them. On the other hand, if in fact the new intensity maxima become very narrow, then we get something else. And now like this. Then I can now actually measure theta much more accurately, the maximum much more accurately. But more importantly, I could have another wavelength. This could be for example, for lambda 1. And I could have another, lambda 1. And I could have another intensity maxima for lambda 2. And I can see both of these because they're each very narrow peaks, right? But if the peaks were very broad, they would overlap with each other. I'd just see one large peak and I would say, oh, there's only one wavelength that's located right in the middle. I wouldn't have the resolution to be able to resolve two different wavelengths that are close together because their peaks would be too close together to resolve. Everyone understand the concept of this? So that's the driving factor in studying the we call it a multi-slit. And a multi-slit is a diffraction gradient. Because typically I'm not going to have 5 or 6 slits, I'm going to have thousands of slits. Right? And what we're going to find is that if I add more and more slits, the width of these gets smaller and smaller, and that's exactly what I want. I want to make the widths of each of those intensity patterns as narrow as possible, right? And that's the goal. So that's the primary thing. Now, the first statement I made, which is the location of the peaks, does not change as we add more and more slits. So and notice that's exactly what you should see here, is that these 3 peaks line up. It's just the width that has changed. Now, why is it that the location of the peaks doesn't change? Well, we start off with light going straight through at 0 degrees. At 0 degrees, all of the rays converge with maximum intensity because all the rays, there's always rays from one slit that travel exactly the same path length as rays from another. They add in phase, and pairwise, they add in phase all the way out. For example, let's suppose, I'm going to imagine there's actually 6 slits here instead of 5. Let's add another one up here. Then slits number 3 and 4, if they were at theta equals 0, travel the same distance to a midpoint on the screen. They would go straight ahead and up a little bit, this one would go down a little bit. Rays from ray number, let's call this slit 1, 2, 3, 4, 5, and 6. Rays from 2 and 5. This one would also travel the same distance to a point in the middle on the central axis. And similarly, a ray from point 1 coming from slit 1 and slit 6 would travel the same distance to the middle of the apparatus at a distant point. And therefore, all of the rays add together in phase and I get a bright spot. And it's true regardless of the wavelength of the light. That statement does not depend on wavelength. It is true for all wavelengths. That pairwise, I can find 2 rays that have traveled the same distance to reach the central axis. By central axis, of course, I'm referring to in this diagram, I'm referring to this point P on the screen right here. Okay? So pairwise, I can always find rays that travel equal distance from each of the slits, from each pair of slits, and therefore they add in phase. Okay, so that's not a surprise. That was true for single slits, it's true for double slit, it's true for 10 slits, it's true for 20 slits, or it's true for 1,000,000 slits. Okay? Now, what is different now, or a little different, I guess, or the same, what if I'm off at an angle where the path difference between light from slit number 1 and light slit number 2, this little element of segment called delta L, which we know is equal to d sine theta. So if I have a multi-slit apparatus and the slits and the spacing between the slits is d, so d was this, which is similar to what we did with the double slit, then and I have that delta L is equal to d sine theta. Right? Whenever the difference in path length between two adjacent slits is equal to m times lambda, I'm going to get constructive interference for those two rays. Right? But if it's true for these two rays, that this one travels, let's say, one wavelength longer than this one, then slit number 3 and 4, this one travels one wavelength longer than this one does. So those two add in phase. And similarly, slit number 5, if I could draw it here, and slit number 6 also have a path, same path difference, d sine theta, and it is also equal to lambda when that's one wavelength difference. Then those two will add together in phase. So 1 and 2 add in phase, 3 and 4 add in phase, 5 and 6 add in phase. Therefore, 7 and 8 will add in phase, and so will 9 and 10, and so will 11 and 12, and et cetera, et cetera. Right? So pairwise, they always are going to add in phase, so I get the same condition of constructive maxima for the N slit. So for N slits, it's the same condition as intensity maximum, the same as single slits, double slits. So I've just shown that the intensity maxima are the same location for a multi-slit diffraction as the intensity maximum for two-slit. Right? One less formula to memorize. Right? Same formula for two-slit works for N-slit. It's nice to know. It'd be very, very helpful. Yeah?
So the distance between the adjacent slits has to be the same as the distance between the two slits and the double slit experiment, is that right?
For the same angle of the maximum, yes, yes. So in other words, if you wanted to have the intensities at the same location, then this distance d between adjacent slits would be the same as that same distance d in the two-slit experiment. Okay? Yeah, yeah, that's right. Okay. So that part looks really good. Okay, so now the only other, so we know this and this works. So and we did it by looking at pairwise comparison and then adding them all together. All right. Wish I had time for a story, but I'll try to suppress it. Okay, so now the one of the crucial questions are, why do these get more narrow? So in other words, the more lines or slits there are, the narrower the piece. Why is this happening? So this is 2 slits, this is 6 slits. Okay, we're having what's going on here. How does this actually work? Let's see. So, not sure I have a slide for that, so I'm going to try to do that on the board. Again, let's start and look at the 2-slit experiment. I wonder if I actually already did the 2-slit over here. Good, we've already got 2-slit. Let's observe one thing about the 2-slit experiment. The 2-slit experiment, the location of the minimum is at lambda divided by 2d. All right, okay? Is lambda divided by 2d. Now, let's suppose that we take 6 slits. I need the eraser here. We take 6 slits. And we want to know what is the angle 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, so here. Here's the intensity maximum. Theta equals 0. Right? Theta equals 0. Intensity I equals I max. I equals I max. Right? For all wavelengths. Now I'll say, how far do I have to move off before this thing falls to 0? Before I get to a minimum. Right? And the way I'm going to do that is by saying, well, let's suppose I go off at a given angle, 1, 2, 3. Let's suppose that I go off at a given angle where the phase difference, so the path difference is d sine theta, right? Same as double slit, but I want the phase difference to be equal to 60 degrees. So I've got 6 slits. So choose theta so that phase difference, delta, is equal to 60 degrees. 60 degrees between, I can't really draw this terribly well, but I'll do the best I can. Okay, if the phase difference between one, we're counting slits this way from the bottom up, right? If the phase difference between one, let's do up here first. If the phase difference between 5 and 6 is equal to 60 degrees, that says d sine theta equals times 2 pi over lambda is equal to 60 degrees. Right? Okay. What that means now is that the phase difference between number 6 and number 3 is 180 degrees. Okay? If the phase difference between 6 and 5 is 60, and the phase difference between 5 and 4 is 60, and the phase difference between 4 and 3 is 60, then the phase difference between 6 and 3 is 180. I've taken the phase difference 3 times. So phase difference between we will say slit 3 and slit 6 is equal to 180 degrees. Okay? If this is true, if I've chosen theta so that the phase difference between this is delta, right? If the phase difference between these two adjacent ones is 60 degrees, then the phase difference between every third one is 180 degrees. Everyone following this? Everyone saying, is this not clicking? Or is this not making sense? If the phase difference between every adjacent one, if this one travels 60 degrees out of phase with this one, and each path length difference is the same, then the phase difference of this being 60 degrees says that from here to here, that phase difference is 120 degrees. And therefore, the phase difference between here and here is 180 degrees. Okay? I just keep adding the same path difference each time, therefore I add the same phase difference each time. I mean, I calculate the same phase difference, I'm sorry. So I calculate the path difference each time, and then I increment it by d sine theta. That stays the same each time. So I've incremented the path length between adjacent rays in the same amount, therefore the phase changes the same amount. Okay, so what happens when I add 2 waves that are 180 degrees out of phase? They cancel, right? Right? So 6 and 3 cancel. Anybody want to guess how, if I add 5 and 2 together, what I get when I add those 2 together? What happens when those 2 waves get added together? Keep going, I heard something. Anything is fine.
180?
They're 180 degrees out of phase. What does that mean when I add them together?
Dark.
Dark. They cancel. Right? 5 and 2 cancel. Right? What happens when I add 4 and 1 together? Same thing, right? Cancel. Okay. So, what I now know then is that this angle, and I'm going to call this theta 0 because it'll be the first minimum. So this would be theta 0. Right? Is going to occur when at sine theta 0 equal to lambda over 6 times d. Let's see if I did that right. This is the condition for the angle that I have chosen. This is theta 0. Choose angle theta 0 so that adjacent rays are 60 degrees out of phase. Right? I choose that, and I now say that 60 degrees is equal to delta is equal to 2 pi divided by 6, correct? So if I solve this for this equation for sine theta 0, then I get that sine theta 0 min, right, min, is equal to lambda divided by 6d. Right? I just solve this equation for sine theta 0. Sine theta 0 is, of course, the minimum. That's where the minimum is. That's my notation. All right? So the minimum occurs for sine theta equals lambda over 6d. All right? Now, let's go back. For two slits, the minimum occurred at lambda over 2d. For 6 slits, the minimum occurred at lambda over 6d. What if I have n slits? Where does the minimum occur?
Lambda over nd.
Lambda over nd. So for n slits, sine theta 0, and by the way, since n is like an order of 1,000 or more, and lambda over d is also like less than a thousandth, this is definitely small angle. So sine theta equals theta, 0 is equal to lambda divided by nd. Right? So what happens now is, what's happening is that the width of where this thing comes back to 0 becomes very narrow, this delta theta. So delta theta is, or delta theta 0 is this distance from the central axis to where it goes to 0, delta theta 0, and this gets to be smaller as n increases. Right? So the way I make the peaks very narrow is to have a lot of slits. That's what this is telling me. Okay? So the first result of all this is that theta 0 is equal to lambda over nd. Okay. Now, it turns out that, and we're not going to actually prove this because I think that, you know, it's something that you either want to know or you want to know the result. So we're going to go to the result. And the result is that when we actually measure, if we measure wavelengths with this method, we're never really measuring the width of the maximum at theta equals 0. This is where all the wavelengths add up in phase. Right? We can't make we don't get any separation of wavelengths at theta equals 0. It's only when you move away that I can separate out. So what is the width of these side fringes? Right? It turns out it's very similar. I'm just going to write the result, but the result is that the width of the side fringes delta theta 0 is is given by almost the same formula, lambda over nd times, or I should say sine theta m, since we're no longer talking about the central maximum, nd times cosine theta m, okay? Where theta m is the angle of the mth maximum for wavelength lambda. Okay, for wavelength lambda, where theta m is the angle of the mth wavelength from maximum of wavelength lambda. It looks very much like theta 0. The width of the central of the central maxima is just lambda over nd, so we end up with an extra cosine theta. By the way, most of the time theta is less than 50 degrees, so this is only going to differ from this by at most a factor of 2. Okay? Cosine theta doesn't, in the denominator, doesn't really contribute much when theta is less than 50 degrees. So since most of the measurements are usually made in that range, it turns out that these two expressions are not that different, okay? But there is a cosine theta term. That says that the width of the nth maximum, so if I want to know what the width of the nth maximum, let's say this was m equals 1. Now I want to go out to, I'm going to stay with red. So this would be lambda 1 for the first maxima. So here is lambda 2. I'm sorry, this is lambda 1 for the second maximum. And then I'll have another one down here, which is lambda 1 for the third maximum. Right? So they increase this way going across. Now, what I'm calculating here is the width, or actually the half width. Theta m is the half width, delta theta m, is the half width of the fringe. Of the fringe. Right? That's what delta theta is. If I want to know the full width, I got to multiply by 2. But delta theta is the angle, the difference between where the maximum is and where it goes to 0. That's the half width of the band. Okay. Is this making sense? Is this right? I'm not sure I'm talking English or Greek up here, so it's English with Greek letters, but I'm hoping you get the English part of it before you get the Greek part of it. Okay, so that's what it does. So yeah, it does lower the width, and notice that the width of each of these lines gets smaller as we go to having more slits. So the density of slits is important. The more dense, more slits you can put in that region where the beam is hitting, the better the resolution of the device. We want n to be as large as possible. Or we can make d smaller too, I guess. But the product of n times d is what's important here. Okay, let me move on. I think this one is confusing, so I'm not going to go there. I made some notes last night. So this is actually what a spectrometer looks like. Those of you that are taking the physics lab this semester are actually doing this next week. I already started. I'll turn the lights down a little bit so you can see it better. You can see that. That's a little better. There's a source, there's the grating, and then you swivel the telescope around and you look at where the lines occur, and by measuring the angle theta, you can solve for lambda. Right? This is basically, these are like your homework problems. You can do it, and you can do it in real life as well. This is a case where, let's say we have a diffraction grating, and by the way, the one in the bottom would have been done with a 2-slit experiment, and the one above there would have been done with one with, well, actually, they're different wavelengths. But notice that the blue and the red are much broader in the bottom one than they are on the top one. But what I'm able to see from this is that if I look at, for example, the top one, I can see the diffraction maximum for the red and the blue. And of course, the red is at 700 and the blue is at 400. And it gives the same locations as we expect from the double slit. Okay, so we can use that formula to do a calculation. Suppose, for example, that I want to know on the previous slide, I want to calculate where is the location, with what angles are the first and second blue, are those blue and red lines occur? So what angle of diffraction gives me those bright intensity lines? Okay, so I'm going to use this formula. I'm going to use the same formula as we've been using all along. And that is that, I'll change the light intensity again. There. I think I'm going to need this later on, so I'm going to leave this up for now, but I have the wrong color. I need black. Okay, so how do I calculate that? Well, let's say I want to know, for example, what is the angle of, suppose I need to know a little more information. So let's suppose that the light pattern for red and blue occur with diffraction grating with 500 lines per millimeter. Let's say 500 lines per millimeter. Okay? And I want to know at what angle is the second intensity maximum. Intensity maximum for the blue light. And if I know that blue light, which I do, has a wavelength of about 400 nanometers, then I can solve this. So I can now say, okay, what I'm really looking for is d sine theta, and it's the second maximum, so I'll call it sine theta 2 maximum, must be equal to 2 times lambda, because for this case, m is equal to 2. Right? So I'm looking at how to calculate theta. Well, it turns out I know everything to calculate theta, because lambda is given by the color of the blue light, which is 400, and I start with a diffraction grating with 500 lines per millimeter, which means that D is equal to 1 over 500 millimeters. Okay. The spacing between the slits is 1.002 millimeters. Right. So, turns out I can solve this pretty easily. So this becomes sine theta 2 maximum is equal to 2 times 400 nanometers, or I'll call it 0.40 microns, divided by D. D, which is 0.002 millimeters, is equal to 2 microns. So I divide this by 2, and I get that this is equal to 0.4. So sine theta 2 max is equal to 23 degrees. Or I should say, I've solved for theta. So theta to max is equal to 23 degrees. So there's an example of using the diffraction gradient. Of course, that to apply for the double slit. So in this particular case, what I'm doing in the solution that the problem that I'm solving is I'm looking at the diffraction pattern for the m equals 2 line for the blue on the upper graph, the upper display. And so I know that if I use a diffraction gradient of 500 lines per millimeter, that the angle at which that intensity maximum would occur on the blue, which is the one I'm pointing to, somewhere I've got my pointer that, has you guys seen my pointer?
On the whiteboard, right behind you, right?
Oh, thank you. So this line right here occurs at an angle of 23 degrees from the center of the diffraction gradient. Everyone see that? All right. So this is a way we can use this to calculate. We can calculate angles, wavelengths, whatever. I could have told you that, in fact, that this, for example, suppose I didn't know these wavelengths. I could have said this occurred at a distance of 5 centimeters from the center, and the distance from the diffraction grating upstream is 2 meters. Calculate lambda. Right? I give you enough information to calculate theta. You know it's the second diffraction maxima, so m is equal to 2. And I now solve this equation for lambda instead of for theta. Okay. All right. So that's an example. So one final example before we stop. We need to do one more derivation, and that is we want to discuss the quantity called the resolution. So the way we're going to do this is I'm going to start with this equation right here. Okay? And this tells me the width of the central maximum, or not the central maximum, the nth maximum, the nth fringe, the width of it, or the half width. Right? Now it also tells me that that any two wavelengths that give theta closer than this amount will be unresolvable. So this is the minimum theta separation, theta m separation for two wavelengths. For, let's say, lambda 1 and lambda 2. All right? This is something to keep in mind, that the width of the peak is also the minimum separation between two wavelengths. All right? If the two wavelengths have peaks that are closer together than this delta m, they will overlap. There is delta theta m. And there's another peak right here, which has a peak that is located, for example, right here. It has the same delta theta m, but the sum of these two peaks gives me that. I can't tell them apart. Right? This is for lambda 1, this is for lambda 2. But if they are different enough, then I can see the difference between the two, but they have to give me angles that are at least this big apart. Now there's a question. There's a simple way of expressing this by doing a little bit of one or two lines of math. Remember that since lambda is equal to, I'll write it a little bit differently, d over m times sine theta, that the difference, delta lambda, which we will say is lambda 2 minus lambda 1, is equal to d over m times the cosine of theta, times delta theta m. Right? And m is for the mth maximum, so I'll put the m subscript here, and I now have a formula that is that looks like this. Right? Now, by the way, this delta theta m is also equal to theta 2, where theta 2 is the second wavelength, minus theta 1 for the mth maximum. So I've changed my subscript a little bit because now delta lambda is the difference between two wavelengths. Delta theta m is the difference in theta. This is theta 1. I'm sorry, this occurs at angle theta 1. This one occurs at angle theta 2. And the separation between these two has to be at least as big as the width, delta theta m. Now, the bottom line is that if I combine this equation with this equation, I can eliminate cosine theta m. In fact, I can eliminate d cosine theta m delta m. And I'm left with lambda 2 minus lambda 1 divided by lambda, and I'll call lambda average, which will be the average. Let's do it the other way. Let's do it the other way. Delta, am I using little deltas? Yeah, there we go. Delta lambda over lambda is equal to 1 over n times m. Okay? So this is the resolution. This basically says that the smallest difference in angles that I can measure, difference in wavelength, the smallest difference in wavelengths, in lambdas, that can be measured is delta lambda equal to lambda times 1 over n m. Okay? And this is equal to lambda 2 minus lambda 1. Okay? So the smallest difference in wavelengths that I can measure is given inversely by the number of slits, because I need more slits to resolve wavelengths that are closer together. And of course, it's also proportional lambda. So this is the formula, and expressed a different way, it's called capital R, lambda divided by delta lambda, which I'm sorry I'm using delta with two different deltas. Let's keep deltas consistent, delta lambda. Although I am using them sort of interchangeably. Lambda over delta lambda is equal to n, number of slits, times m, where m is equal to 1, 2, 3, etc. Right? That's the order of the French. So this is a shortcut version to the end result, which is that the resolution improves with the number of slits. Okay? Sort of intuitively, that's what we've been talking about the whole hour, is the width of these maxima gets smaller and smaller as we have more and more slits. Okay. We've already done this one. And the result that we came up with, as the number of slits becomes large, the widths of the central maxima and all maxima become very narrow. The resolving power to measure two wavelengths by separation delta lambda is given by the formula that you see here, lambda over delta r, which is called the lambda over delta lambda, which is called the resolution. Okay, we've got one example. I mean, I can hold this to next time, but you can also, this is on Blackboard. You can read this one yourself. This example is also worked up in Gene Coley, by the way. I might do it if I have time tomorrow, next time, but basically, it's basically saying, calculating how many slits are needed if I have two wavelengths that are separated by only by half a nanometer, that's a very small amount. And then the calculation is just using this formula. But you should look at this yourself on black. I don't need to go through every one, but this is exactly an example of using this equation. Okay? We'll resume next time, finish up chapter 36, I hope, and we'll be on schedule. Okay. See you in 2 days. Everybody stay warm.